presented by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Hello everybody! I hope everyone's having a beautiful day. I want to welcome you on to what should be the last stream for January 2023. I hope you're having an amazing day. And please, if you're watching this live, please feel free to join in the chat where you can ask questions, chat about all sorts of other stuff. And of course, if you have questions during the lecture, please drop them in the chat, okay? I usually am very happy to answer your questions. Likewise, I must stress that if you're in the chat and you're watching or asking questions, I get really excited today. If you find yourself wanting to ask questions, just drop in the chat. If I can address it while I'm talking at that time, I'll address it. If it needs a little bit more time to dissect it, I'll talk a little bit more about it when we get to our kind of like the next kind of intermission in between the segments of the lecture. I must stress that the lectures that we do here, they're done with everybody involved. So please keep in mind that. Another thing I need to keep in mind and also mention for you is that if you want access to the notes from today's lecture, they'll be available on Patreon and Subscribestar at the supporter access tier and above. So if you're looking for the full examples, you want to see how some of the elements beyond just what we talk about here. I also include additional examples if people are asking for them. I'm usually quite happy to look into those. Oh, hey, Miss Kitty's here. Hello, Miss Kitty. What you doing? Yeah, she's having a pretty good day, I think. She's got a pretty bow tie. But before I get started, I have one item that I need to address while Miss Kitty's enjoying herself here, okay? One important item is that I want to figure out and recalibrate our schedule live. In particular, I want to make sure that I'm able to go live at times that my audience might prefer a little bit more than what I currently may be doing. I must stress that generally people show up and have a great time. But the thing is, I want to see if there's any preferences of times people might be available. So if you're curious about this, I've put a survey on the social media pages, and also depending on where you're watching this, it's in the link in the description. So if you complete that, it gives me some feedback on your availability so that I could best schedule our live schedule, which I must stress that the schedule kind of builds up quite quickly. So it helps me get some information in advance when I'm planning for the upcoming month. Why? Because usually when I schedule things, usually they're figured out a good chunk or at least a couple weeks in advance. So I try to do this in advance. So this is helpful feedback for me, but also it's an opportunity for you to give me some feedback on whether you're enjoying what we're doing here. Likewise, it's also an opportunity to let me know if there's any topics you're interested in beyond more specialized topics, or perhaps specific requests that you may have. Say that would be something that maybe at the supporter access at Patreon or Subscribestar might be a bit more appropriate. But either way, I just want to know a little bit more about what you're interested in and what your availability is. So please complete the form. It only takes about 1 or 2 minutes, okay? So I'm looking forward to hearing from you. Likewise, the mailing list was just about ready. I know it's taken a little while. It's because there's a bunch of other things that came up at the same time. It also requires me to set up a few technical things that I can't talk about here on stream. Miss Kitty, you want the notes? It appears she wants the notes, but that means you have to support on Patreon, Miss Kitty. Yeah. Yes, Miss Kitty. Yes. And as people might know, the quality of the work that we do here is meant to be high quality. and we have ourselves a great time. So, and I must stress that those two things don't have to be exclusive to each. Like they could be happening at the same time. So this is one of the main arms for why I do what I do. It is to provide affordable, high-quality computer science educational content that otherwise is rather difficult to get your hands on without spending a lot more money. Just speaking professionally. So, Miss Kitty, it's time for you to go hang out somewhere else for now. Because we're going to be talking about a rather interesting topic here today, Miss Kitty. Miss Kitty's trying to eat the notes, okay, everybody? That's how amazing these notes must be. Why do you want to eat the notes, Miss Kitty? What's happening? I have no idea, Miss Kitty. Miss Kitty, what you doing? What you doing? Don't make me shock you again. She got a pretty good zap a little moment ago. I just shocked her ear. Miss Kitty, it's time for you to go. Come on. Come on. Come on, Miss Kitty. It's time to go, Miss Kitty. Miss Kitty's a little crazy today, as you might guess. She's gained an extra sense of confidence in the last little while with her little cute bow tie. But anyways, we're gonna let her have some fun. I'm sure people won't mind watching a cute cat kind of run around. Miss Kitty sort of does that sort of thing. But I'm just trying to think of anything else off the top of my head here. I think I've covered everything that we need to know about today. So we're going to get ourselves started here today. We're going to be talking about non-deterministic finite automata. But to do this, we're going to talk about the concept of non-determinism, okay? So I'm just going to grab a couple of quick things here, because Miss Kitty seems to have kind of thrown a few things around. And that was me spraying Miss Kitty with water. She'll be back. I have a feeling she'll be back. Anyways. That being said, one other thing I need to mention. I have to mention this every once in a while for anybody that's new watching. Sorry, like I said, sometimes we have ourselves a little bit of fun here. Is when the chat is available on the screen, that means that you can hear the text-to-speech from some platforms, so such as Twitch. But also keep in mind that just because the chat isn't visible, I can't see or hear it. I have a monitor right here where I could see everything that is interacting in the chat. So please be aware that if you ask a question or something like that, it doesn't have to have the chat visible on the screen, nor do you have to hear anything. So just keep that in mind. So I just need to mention that for those that maybe need to just be aware that the audio and visual cue of the text chat doesn't mean that I'm asking for a question at that time. It may be, it may not be. Just the point is we can hang out in the chat anytime you like. So anyways, enough of that. Let's get into today's topic. We're going to be talking about non-deterministic finite automata. Now, to do this, I need to remind you what a deterministic finite automaton is. So recall that a deterministic finite automaton has a set of states. It has, of course, it has a bunch of fun things, right? It has a set of states. It has, what else? It has an alphabet, a set of input symbols, right, Miss Kitty? It has a set of input symbols, but it also importantly has a transition function that takes in a state and a symbol. Sorry, Miss Kitty, you're really having a fun time here, aren't you? And you're all wet now. Miss Kitty, you're getting stuff wet here. This is Miss Kitty. Come on, you can go down. For now, Miss Kitty is disrupting the lecture. She's gonna have I'm gonna have to do the fatherly thing and have to make sure I have to talk with Miss Kitty about her behavior. She got my notes all wet. I think it's best we start over. But we're having ourselves a blast, right? So that's the point. So please just don't look at this and be like, oh, Dan just bought it. It's like, no, we're having ourselves a fun time here, okay? Please just keep that in mind. The point of having Miss Kitty around is to have a blast, okay? I know that some of these topics are a little bit hard to digest without some form of, well, actually, I wouldn't even say it's some form. It's just having some engagement from the lecturer, okay? Miss Kitty, go away, please. Just for now. You can come back in a little bit once we get into the juicy bits about non-determinism. Everybody here needs to make sure that we understand carefully what that means, because it is not I would argue it's not a simple concept. It's something quite alien in many regards. So let me just walk on over here. I'm just gonna tell Miss Kitty to go find somewhere else to play for now. She'll come back later. And yes, I sprayed her again. She had it coming, okay? She was trying to eat the notes, okay? They were very delicious. But anyways, let's get to where we're talking about things here today. So today we're going to be talking about nondeterminism and nondeterministic finite automata. So to do this, I need to remind you of what a deterministic finite automata is. So first, recall that this is an abstract machine, what we would call an automaton, that has some features. Namely, it has a set of states. The machine can be in one state at a time. Namely, what happens is it processes an input string, and the string itself is a set of input symbols that are read by the machine. Then this machine moves from state to state depending on what current state it is in and what input symbol it reads, the transition based on what is called a transition function into potentially another state. One thing I also need to mention is that the machine also begins in a start state. So it has to start off in a state and then it reads the string one symbol at a time. And upon reading all the symbols, it may be in what is called an accepting or final state. So there's a set of these states called the final and accepting states. And if upon reading the input string, it is in one of these states, the machine accepts the string, otherwise it rejects the string. So on that, let's talk a little bit about a little bit of a higher level question than the things we've talked about previously. So, just a couple of questions. So, one question that I like to usually bring up, and it will allude to a lot of things we're going to be discussing among our lectures on theory of computation. But it's a general theme, but I'll specialize it for DFAs. So if we give DFAs more features and functionality, which I must stress at this stage is not really quite clear what exactly that means, but I want you to imagine like you had a physical computer. What are some things that you can do with a computer that, if we're already at this stage, we're dealing with a machine with a finite number of states, it doesn't have any memory per se, it only remembers the current state. That's the only thing it knows, okay, as a machine, if we're trying to anthropomorphize the machine. It has a state that it is currently in. That's all that it currently knows, okay, other than where to go next based on a transition function, which is often implemented as a table or represented as a graph, a directed graph. So, and functionality. So the first question is, if we give DFAs more features and functionality, will resulting machines, that means that once we've added these extra features to it, well, resulting machines be able to recognize other languages. So recall that we said that if there exists a deterministic finite automaton that recognizes a language, meaning that I imagine I have this language, it's a set of strings, and I'm able to say, hey, look, for every one of those strings, my DFA accepts, and any one of the strings that are not in my desired language that I want to recognize, they get rejected by the DFA, but it has to be all of them in this language, and it has to reject all others, right? That is what we would describe as a regular language, those that are recognized by a deterministic finite automaton. That's how we defined it previously. So if we give more features and functionality, will we be able to recognize other languages? So that's an interesting question, because namely, we didn't really address this at all. Now, ultimately today I'm not going to be addressing the second question here, but we'll talk a little bit more around the first question. Are there other languages? Are there other languages than the regular languages? See, these are two rather interesting questions, right? So the first question is really about, if I take my DFA and I give it some more computing power in some way, shape, or form, whether it be memory or some data structure or some way that the computing machine actually operates, will I be able to recognize other languages? And the second one is, okay, are there other languages that exist that a DFA can't recognize? Now, we're going to eventually address question number 2, but I want to explore question number 1. Now, the short answer is that it's complicated. Namely, that it depends on what these features and functionality exactly are. So sometimes yes, sometimes no. And that's going to be a very nuanced thing that we're going to have to explore in the upcoming lectures. So we're going to focus in on this question. Namely, can we supercharge our deterministic finite automaton so that it's able to recognize other languages? Or is this prospect fruitless? Meaning that if, depending on what features I use, it actually can be the case that they still only recognize regular languages. So we're going to see that the answer to this is going to be sometimes yes, sometimes no. So to explore this idea, namely one example of how we can add more features and functionality to a deterministic finite automaton, we're going to explore an idea called nondeterminism, which is a broader concept in theory of computation, which at first will sound really strange, but if you think about it, it's a rather natural idea for how you might generalize computation. But it's going to sound really, really strange, some black magic level stuff, okay? So recall that, as I mentioned, in a DFA, so let me just draw a picture of a DFA, just to help us kind of really, so just remember, how does a DFA process a string? So let's revisit this. So I'm going to use a DFA that we previously had derived together. So I'm going to draw its transition diagram. So it's going to have 3 states. So the final state is going to be Q2. And recall that this DFA was able to detect if the substring 0, 1 exists within the input string. So I believe that's everything here. Miss Kitty, did we get everything? I think maybe so. She seems rather content about this. She's quite impressed. But anyways, let's talk about how an input string would get processed by this DFA. So suppose that the input string W is 10011. So for context, we called this DFA M sub. So if you're wondering what this was, we called it M sub in our previous lectures. So I want to walk you through, you'll see why I use that word I use it quite deliberately. Why? Let's go for a walk through how this DFA gets processed. Well, how does the DFA process W? So what's the thing it does? So first, remember, it starts off in Q0 because you see there's start here pointing at this guy here. So I start off here. Well, remember, it reads each one of the symbols from left to right. So it'll start off by reading 1. So yes, Miss Kitty, yes. It's going to read 1. So it starts off at Q0. It reads a 1. So notice that the transition from Q0 on reading 1 is to go back to Q0. So it just stays in Q0. So it follows along here. So imagine it's just like I follow it with my finger. Then next I read the 0. So then I transition from Q0 on 0. It tells me to go to Q1. And then I read another 0. So M sub will then transition, follow along this transition here, back to Q1. It reads a 1. Then it transitions on symbol 1 from Q1 to Q2. Notice that the transitions here is either 0 or 1 here. So I'm just going to follow with my finger up around, and it ends ultimately up in state Q2. So notice that in a DFA, we have defined transitions on every one of the input symbols. In this case, there's 0, 1, and all the states. So we would say this is deterministic because every time I give you one of the input symbols, I could tell you, given a state, that it goes into another state. It's deterministic. But it's only one state. It exactly is defined by a single state. But for those that know a little bit about graph theory, for example, you might look at this directed graph with loops in it. And what I did here, so notice that I follow along with my finger. It shows you how I process the string. But do you notice that it is what we would call in graph theory a walk? So this is a walk in this directed graph. Exactly, Miss Kitty, it's a walk. Some might refer to this as a path, specifically not necessarily simple path. But the point is that it's a walk, right? So a natural question is when, and this is actually perfectly characterized by the transition function. So notice that I'm allowed to go on a state with a symbol. I go to another state. It may be the exact same state. It may be a different state. But the point I'm getting at is it's a walk, right, like this. This is how computation gets carried out on a DFA. It's a walk. So this is characterized by the transition function and what state I'm allowed to be in. So those are two pieces to how this works, okay? So please just keep in mind these two things. So processing a DFA is a walk in the transition diagram. Likewise, it has only one current state. And remember, we talked about these, we had exact definitions for both of these things. So remember, these are characterized by the transition function. So these are defined by the transition function. And specifically how it computes also is defined by what? The extended transition function. So this is defined by delta and delta hat. And we've defined those for the DFA in previous lectures. So, can we do anything to delta and delta hat to supercharge our DFA so that perhaps, I'm not saying that it will, most certainly I'm not saying that, I'm saying it may, possibly, this is a concept we're going to explore, right, Miss Kitty? Right? It's going to be delta and delta hat, right? We're going to be looking at those. Do we get any more computing power by doing something with delta and delta hat? And I'm not saying, and remember, we're going to be using our imagination here a little bit, but some of these ideas do have core concrete meanings. So here's a what-if scenario. So what if the machine could transition to multiple states, upon reading a symbol. So remember, in our DFA, we have a current state that the machine is in. So instead of it just being one state, perhaps it might be a set of states instead of just one. So perhaps we have that. Then, perhaps the execution of the DFA, which no longer would be, right? Because it has to be in one state currently at all times. Perhaps the execution of the DFA is no longer just, I'll use just in quotation marks, just a deterministic walk. So this might perhaps give us some more versatility for how we can describe languages with the machine. If I don't just have it where it's just in a current state, what if I'm allowed to have the machine be in multiple states at the exact same time? So I must stress, for somebody that may be more acquainted with programming or things like that, this idea isn't really too strange to have the concept of like variables that all could be in have different values. But I'm literally meaning the machine state, like as a whole. It's not just allowed to only have one current state, it's allowed to have many current states. So please just keep that in the back of your mind. That intuition though, however, will be helpful when I start giving some intuitions around a concept that we're going to explore now at a higher level, and then we're going to see some examples here. So please just keep in mind, it's going to be a little bit for you to chew on for now, and then once we get to our definition of our DFA where we allow this behavior, we'll see an example and revisit how these two intuitions exactly work, okay? But the point I'm getting at is the minute you allow this to be the case, now you're playing in the land of non-determinism, okay? So we will explore the concept of non-determinism. And we call it that, non-determinism. So we call it non-determinism because it's not deterministic, right? So remember, deterministic means I can go from it's exactly defined that I go from one state to exactly one other state, right? However, that is not true anymore if I allow this to happen, right? It's non-deterministic. But we gotta think about what exactly this means. So I'm going to give you a couple of intuitions for how a machine like this might behave, okay? So let's talk a little bit about non-determinism before we get to start talking specifically about DFAs. So this is a powerful but interesting concept from theoretical computer science that permeates much of the complexity theory literature. So please be aware that this is not just a concept I'm picking up and saying, oh yeah, this is just about deterministic finite automaton. No. If you want to study different computational complexity classes, this concept creeps up all the time. For those that are enthusiasts of, say, algorithm analysis, you may have heard of concepts like this. Say if you really are really enthusiastic about the subject, you may have heard of something like PNP. NP stands for non-deterministic polynomial time. That's a set of decision problems. So I must stress that this non-determinism concept is the exact same one there, okay? So just be warned. This is not just a very specialized version of something else. This is actually a concept that permeates a lot of theoretical computer science. So it's another way of thinking about computation. It's another way of manifesting computation. Okay? So it will sound really strange at first, but I assure you it's a very natural idea once you get a grasp of it. It's just that we're used to thinking about a machine being in a current state, and then when you do something, it goes into another state. Here, that is not necessarily the case, okay? So we will next consider non-deterministic machines. Non-deterministic machines. Machines where several states may be selected for the next state when reading the input. That's one thing, is that, remember, it's going to be that we can select from several states. Now, you could literally select on all of them, but well, certainly there's an intuition that's quite natural that allows you to just think about this as if it's selecting specific states, as we're going to talk about shortly. The other thing I really want you to know about this is that it generalizes the concept of non-determinism. Non-determinism generalizes that's a really sad looking E over there. Non-determinism generalizes determinism. So it must be stressed that if I give you a finite automaton that is non-deterministic, which we'll refer to these as NFAs, or non-deterministic finite automata, or automaton for singular, or NFAs for plural. I should be a bit more precise about that. So in the case that we're generalizing like this, when we introduce these couple of features, we're going to be talking about something called a non-deterministic finite automaton, or plural, a non-deterministic finite automaton. Sorry, automata. Sorry, I'm getting really excited here. The point I'm getting at is that, think about it. Why would this be true that non-determinism generalizes determinism? Well, remember, in determinism, the idea is that you have a state that your machine is currently in. You process something. How many possible ways could something happen? It's exactly one, right? It specifies exactly what direction you're going for the next possible state, right? In non-determinism, that's not true. In fact, you're allowed to have a set of states. Do you notice that if my set of states only had one state in it, it's that, right? So that's what I mean. So for instance, so every DFA is what we're going to define in a little bit, a non-deterministic finite automaton, which we'll abbreviate later as an NFA. So I'm going to give you a couple intuitions around how these two features might exactly work once you allow this to happen. Because remember, our machine is in multiple states now, right? It's multiple states at the exact same time. So what does that mean? And how can we kind of grasp around that, how that works? Because remember, in a DFA, just in our discussions as we have so far, the DFA will process the input string, right? Just in our specific context. Upon reading all of the symbols in that input string, what does it do? It either does what? What does it either do? It either accepts or rejects, right? Now, in this specific setting, that means that there's going to be a finite number of moves or transitions that have to occur. And ultimately, if there exists a path of execution, a walk, akin to our example, to a final state upon reading the input string, it doesn't really matter what all of those other states that the machine is currently in are, right? However, there's an asymmetry here. If there exists no walk from the start state to the final state upon reading the input, then most certainly any one of the possible paths execution leads to a rejection, right? So any one of them is like I'm making a very bad guess, right? So there's kind of two ways I can think about this, at least. There's actually other ways as well, but I'm going to keep it rather straightforward here. So for those that are thinking, oh yeah, this is like something I have in the back of my mind, it might be related to something similar to the second intuition I'm going to provide for you. The first one I like to start off with because it ultimately is about the functionality of the machine, right? So you got to remember, the machine is in several states at the exact same time. So when it reads the next symbol, for example, or reads the input, it can transition into several other states, right? But what matters upon reaching the final state? If it read its input, as in the case for a DFA, it has to accept, right? However, it could be the case that many other so-called paths or walks might not lead me there, right? So the first intuition I would like to give you is this idea of perfect guessing. Now, from a computational complexity standpoint, this perfect guessing intuition is rather similar and closely related to the idea of verification. So you may have heard of this concept before. It has very close relationship with what I'm going to describe here next. So the machine is able to guess choices that lead to a final state. So you might say, yes, Dan, well, that seems, so you're saying that when it transitions, it's allowed to guess choices from those transitions, and that ultimately is a walk? Yeah, that's what I'm saying. That's what I'm saying. Because remember, when a transition occurs, it could go into several states. Now, you want to imagine like I'm looking at one walk from one of the branches of the execution. Because remember, when it's in several different states, all of those, it may transition onto other states, right? So the thing that matters is that there exists a walk of the execution of the machine that it accepts, right? If that is the case, right? Now for a DFA, it's rather straightforward because notice that we read one symbol at a time. So it means that any one of these walks, possible walks, or passive execution, all of them will terminate. But if we add more features to the DFA, beyond what we're going to talk about here, that's certainly another topic, it may be the case that some of these walks may go on forever. So, like I said, there's a little bit of an asymmetry here. So please just keep that in the back of your mind. So if there is at least one selection of guesses that leads to the machine being in an accepting state, the machine guesses it. That's the weird part about this, okay? The machine guesses it. So just to be a bit more precise about what I'm saying by guessing is that when you have the possibility in this context of our finite automata, you have the concept of transitioning to another state, right? So you can imagine I am guessing, performing my walk, and if there exists a way for this walk to reach a final state upon reading the input, it will guess it. Now, I will come back to why that's a little strange at first and why you'd say, Dan, that seems a little... Is there something up here today? The machine guesses it. However, if there is no way to guess to reach the accepting state or unaccepting state, it rejects. It rejects. Namely, if you're wondering what that might mean, at least in this intuition, it guesses any of the wrong guesses. So when we see our example, I'll indicate to you what I mean exactly by this. But please note that if there exists a walk that traces the execution of our finite automaton, it will be that if there is such a walk that leads me to the accepting state upon reading the input, this non-deterministic machine will be capable of just perfectly guessing how to get there. But if it does not have any way of doing that, it just simply guesses one of the wrong walks, okay? Because think about it. What would this mean then? And this sounds like some black magic stuff, okay? It sounds a little bit strange. Has anybody ever heard, it's like, can you imagine I give you an arbitrary input and this machine is capable of perfectly guessing which states the transition into to get to the final accepting state upon reading the input. So remember, it may not even know. It doesn't know what the input is in advance until it's being provided it. What would you call this? Well, there's a fancy name for this, and If but that this ability, and this is why I refer to it as magic, okay? It sounds like magic because it is magic, okay? As far as we know right now these days. The ability to provide guesses that lead to an accepting state like this is essentially what? It's like I knew the future, okay? That's where I'm going with this. Is the ability to know future events, which is magic, right? Like we don't know any way to do that. Which is essentially clairvoyance. So this is the fancy name for what I just described. It's essentially clairvoyance. So this is the ability to know the events of the future. I know, it's pretty heavy stuff, right? So this is one way we can imagine the non-deterministic machine operating. I'm going to show you another one for those that maybe are thinking about a physical device. Now, most certainly, the minute you start hearing about this, you're going to be like, okay, Dan, that sounds like it's really, really inefficient to do. Because it is. In fact, to the point where if you want to, and keep in mind, we're only still talking about finite automaton here. We're not talking about anything more general than this. Just be very clear. So we have to be very careful when I talk about this next one here. So we're talking specifically, you're going to find this intuition helpful as well for how you might view this. I would argue that this intuition will remind you a little bit more about the formal definition we're going to see shortly. So another intuition is thinking about this as massive, or so massive, I'll put in parentheses here, parallel threads. So you can imagine that the machine takes and manages a whole bunch of threads that are happening in parallel with each other, okay? So now you might say, Dan, that sounds kind of neat. Like you have it where it transitions into multiple states. So they're all in those states in parallel. So if you're familiar with parallel computing, this might be like a very natural thing to think about. That you imagine that it's like if I took the machine, encoded it into a computer program, and distributed it across cores, and now each one is in its own state in those literal way I'm describing. So that sounds neat, right? So this is a bit more realistic. So it's a bit more realistic than just simply this. So we can think of the machine being in many states at once. Similar to the first thing I brought up, many states at once. So this is a bit more realistic. So I'll put in quotation marks the bit more part. The bit more realistic. So when the machine reads a symbol X, it spawns. So now this is the part where you're going to look at me like, hey, yeah. It spawns independent threads for each state it transitions into. It transitions into. Or 2. I'll just say 2. Transitions 2. So, if a thread finds no transition, for the given symbol, that thread ends. So that thread ends. Some would just colloquially refer to it being that the thread dies. I don't claim it to be a technical phrase, but most certainly if you talk to people about multi-threading or parallel computing, they'll be talking about how you fork into threads and the thread might die. And so just keep in mind, multi-threading, parallel stuff, they're not necessarily the same thing. They're actually quite different in many regards. But the point is that we have this thread of execution, like our walk. So every single time there's a transition that occurs, you're going to spawn more threads on that current thread. So if you're thinking about this from an actual physical implementation of this thing, it's almost like I'm going on a journey. Every time I can take a fork, I literally make it so that there's copies of me for which I am doing both of them in parallel. Okay, so you can see how quickly a task of simulating this can become very inefficient. So the machine accepts. So the machine, that says an end there. The machine accepts. The machine accepts if at least one thread is in an accepting state after reading the last symbol. So remember, this last symbol business, this is specifically for finite automaton, or finite automata, sorry, I should say for finite automata. If we were talking about a much broader concept of a model of computation, one of our abstract machines, it may be the case that the machine actually doesn't finish processing upon reading the last symbol. So in our sense, if we did something like this quite literally, it will be, in matter of fact, that it will eventually terminate. It's just that you can imagine, I just want you to imagine, once we see our example, you can imagine cases where a simulation like this of the non-determinism, which is what it is, you can see quite quickly that this is going to blow up quite quickly if you have a machine with many, many transitions. So those are a couple of ways of thinking about non-determinism. Let's define now using these ideas, I'm going to talk and define now the concept of a non-deterministic finite automaton. So let's bring this idea into the context for which we were discussing and define it formally. So I know that this might be the first time you've ever encountered this phenomenon before, or phenomenon, depending on if you think of it as a family of different interesting theoretical concepts, or just one. This may potentially be the first time you were encountering this idea, so I want to be a bit careful about this and walk through carefully what's happening. So I'm going to define this for you. So it's going to be our first machine that we're defining here that is non-deterministic. Purely in the sense that it's a broader concept. Remember, all DFAs are going to be one of these machines too, just with a slight specialization. We're actually going to see if there's something interesting going on about that, but that's a whole other discussion for another day. So So we're going to define a non-deterministic finite automaton, which I'll abbreviate as an NFA. So this is, again, another quintuplet. Sorry, a quintuple. I'm thinking of kids for some reason. Not a quint. So an NFA is a quintuple. So we're going to have how many tuples? 5 tuples. So for the NFA, it is a 5-tuple or quintuple A. So our machine's going to be called A here. It's going to have 5 parts to it. It's going to have Q, sigma, delta, Q0, and F. I said a quintuple. So all of those will look rather familiar to you. So let me, and the reason why I wrote it over there like that is because you had actually seen a definition that's just like this one. So making a lot of room for it isn't necessary. So naturally the Q is a finite set of states. It's a finite set of states. Sigma is a finite non-empty set of input symbols. Now, before I get to the transition function, which as I alluded to, that's the one that's going to be very interesting for us, because it's going to characterize non-determinism, right? You can tell just based on my excitement here. So Q0 is naturally the start state, so you need have one state. It's always going to be one of these called the start state, as we discussed previously. Start state, and F, similar to the DFA, is going to be some subset of the states, where it's a set of final states or accepting states. So I'll usually refer to them as final or accepting states. But the last part, delta over there, delta is a transition function, right? But we already talked about how this one's going to be a little different than before. It's non-deterministic. So this is where the definition is going to differ, aside from how it computes using this information. That takes as inputs or arguments a state and a symbol. So it gives you if you're at a state given a symbol, presumably the next symbol you're going to read, then it returns. So it's going to return, instead of just a state, it's going to return a subset of the set of states. And a symbol, then, so delta is a transition function that takes as inputs a state and a symbol, then returns a subset of Q. So for those that want a more formal way of writing this out, what I'm saying is delta is the following. It's a function that, given a state and an input symbol, it outputs a subset of Q. But what's a subset of Q? It belongs to something we refer to as the power set of that set. So this is the power set of Q. Power sets just simply contain all possible subsets of the given set. So as a quick example, the power set of the set ABC. Well, this is just going to be, one subset is the empty set. Another subset might be A. Another subset may be B. Another subset may be C. It lists all of them, right? So it's going to have AB, then it has AC, then it has BC, and lastly, it has ABC. Right? So let's see, we got all the ones, 1. So this would just simply be, then we have AB, AC, BC. I think I got all the possible ways of listing out the subsets for all 2 elements that I can pick, and I have all 3. So notice that this is what a power set is. So all it is just giving you one of these subsets, which naturally makes sense because we're simply talking about, we're quite simply talking about some subset of the states. And as we said, it's going to be allowed to transition to a set of states. Any set of states would be any subset of the states. Is that clear, everybody? So remember, it's just going to take in a state. So remember, this is a state, an input symbol, and it gives you a subset of Q, which will be contained in the power set. So let's do an example. And remember, we could use a lot of the, one thing I really want you to know about when it comes to talking about how we can represent the NFA is it could be that you could use transition tables, transition diagrams. Everything we've talked about previously for DFAs, we can do with NFAs. Just now the main difference is now that we have a set of states as opposed to just a single state. So I'm going to illustrate this definition by using an example. So consider NFA M. So I'm just going to refer to it as M. So I'm going to use the formal description of the NFA first. And then I will give you how I'd represent this with a transition table and then with a transition diagram. So let's see what happens. So I'm going to define all of these for us, for example. So remember, Q is a set of states. So this NFA is going to have 3 states, Q0, Q1, and Q2. So that's our set of states. Next, I'm going to define the input symbols. I'm going to make this NFA work over binary strings. So the input symbols are allowed to be used are 0 or 1. Now, the transition function now, if I wanted to list out all the possible transitions of my NFA, what I would do is I would give you each state with an input symbol, and I would list out the subset of Q for which those are the states that we could transition to. To avoid space usage here, instead I'm going to draw you out the transition table. So please keep in mind, if somebody asks you for the formal description of the NFA, they might be asking for the explicit definition of the function itself. However, often when you're designing NFAs, it's usually the case that they usually just want to know what the transition function is, for which can be sufficiently described using a transition table, for example. So it's transition table. So I'm going to do the transition table as follows. So again, like we've done before, we are going to list as columns the input symbols, and we're going to have the 3 states. So we're going to have 3 rows below Q0, Q1, and Q2. And I'm going to now have to describe to you when I'm in Q0, when I read a 0, what happens? Like which states am I going to transition to? Remember, now it's not just a state, now it's a set of states, namely a subset of Q. So in this case, what we're going to do is we're going to have it so that if it's in Q0, it reads a 0, it's going to stay in Q0. So notice I'm using curly braces to indicate that it's a set, as opposed to just being a single one. So in contrast to this, I'm going to make it so that if it reads a 1, it can stay in Q0 or it could go into Q1. So notice now I can list more than one state. So if I'm in Q0 and I read a 1, the machine is capable of being in Q0 and Q1 at the exact same time. So for Q1, I'm reading a 0, it will go into Q2. And remember, because, as I said, it could be any subset of Q. That includes the empty set. So it means that if it has nowhere to go, meaning that upon reading that symbol, if it's in that state and transitions to no state, it's the equivalent of a thread dying in the intuition we had for the parallel threads intuition. It means that that thread just gets killed. There might be potentially other live ones that can continue the execution of the NFA. For Q2, if it reads a 0, there's no more. There's no more. And upon reading a 1, it stays in Q2. So this is the transition table. I haven't labeled a couple other things quite yet because I haven't told you what the start state is and the final states are. So I'll just write them over here. So Q0 is the start state. Actually, you can see right here it says that this is the start state. So let's just indicate that with an arrow in the transition table. I was about to say that we didn't know yet, but it's sitting right there, right? And now we got to define what F is. So F is going to contain only one final state, Q2. Keep in mind, I can have multiple final states. So it means that in my transition table, I would indicate that for Q2. So there's our transition table for this NFA. Let me draw the transition diagram so you can see what this is all about. But to do it, I'm going to draw it over here. So let me just make some space over here, and we're going to draw it here together. So now we have the table. You might ask, okay, so how exactly does this work? So let's see. So we're going to have 3 states, right? Q0, Q1, and Q2. We know Q2 is a final state, so I'm going to double circle that. If I had more final states, of course, I would double circle those. And naturally, Q0 is the start state. What else? What else? Well, let's go through our transition table and label everything else, okay? So for Q0, it remains in Q0. It remains in Q0 upon what? Well, it stays in Q0 when I read a 0, right? But when I read a 1, notice that I have Q0, Q1. So it means that it can stay in Q0 upon reading a 1. But also it means that it could transition into state Q1 as well on what? A 1. So notice now that I can have it where if I read a 1, it can stay here, but also can go over here at the same time. So you're going to see what I mean by this shortly. So next row, we have Q1. It goes into Q2 upon reading a 0. And it doesn't do anything for reading a 1, so I don't label that. So this is one thing you'll have to notice that's a little different here for an NFA, is that it won't be that the transition diagram exactly has a directed arc, or arc for short. Actually, I'll just call it an arc. I mean a directed edge versus an arc. You'll notice here that if I simply have no transition, meaning an empty set for the transition, it's just not labeled here. So whenever there isn't an arrow I could follow, if I imagine my fingers could potentially spread into many other fingers, if there isn't one, then that finger that's following along, it dies. It's sad. It's a very sad thread. Last row, no transition on 0. On 1, it stays in Q2. So this is the transition diagram for M. So it's our transition table. This is the transition diagram. So now I want to do some tinkering around here before we get to a formal definition for the computing of an NFA. It will remind you a lot of the definition that we had for the DFA's computation. However, since now I could transition into multiple states, it's going to get a little weird, okay? But just because it's a little bit different doesn't mean that it's not like legit, okay? It's still very much something you can exactly specify in a mathematical way. So I have my transition diagram here. I thought it'd be a good idea I show you what happens when I feed a string to this NFA and see what happens. So I'm going to give you an intuition about both of the things we were talking about, namely when we had the perfect guessing intuition and also this massive parallel thread intuition. So suppose that I had it where the input string was 0, 1, 1, 0, 1. So suppose that W is equal to 0, 1, 1, 0, 1 was fed to M. So let's walk through what we just talked about non-determinism. So it starts off in Q0. It reads a 0. Reading a 0 means that it's going to follow this transition. Notice that there isn't more than one transition. So upon reading a 0, it's going to go and stay in Q0, right? So this is the first symbol being read. Next, we're going to read the 1 next. So M is going to read 1. However, there's something else that's going on here. It isn't just going to be staying in Q0, or it's only going to be staying in Q1, at least if we're thinking about our second intuition. Instead, what happens is it's going to spawn 2 threads as opposed to having only 1 thread. So it's going to have one where it's going to stay in Q0. It's going to have one that's going to stay in Q1. So notice now I have a set of states that is not just one state anymore. Now I can have potentially more states. So one thing I should acknowledge for you is that if we have multiple states, even though the intuition of the second kind would say that, oh yeah, they're all like different threads. Keep in mind that the computation itself, if you land up in a state, upon reading a symbol, and as per what we're doing, one symbol at a time, it doesn't matter if you have 5 threads that all are in the exact same state. It's like if there were just one state. Just like I said, it's a set of states. So it doesn't matter. This is just to help us visualize this. So when I read the next one, so I'm going to read the next one. Well, when it's 1 in Q0, what happens? Well, notice that in this guy, so currently, if I'm in Q0 and I read a 1, what happens? Well, this, as we had before, it spawns such that now it's in both states. However, there's this one right here, the one that was currently in Q1. So this thread here, notice that there's no transition out of Q1 or even retaining it in Q1. So this thread dies, it ends. So then we have the next read. The next read will be on a 0. So a reading 0 in Q0 keeps you in Q0. If I'm in Q1 and I read a 0, we go to Q2, right? Because if I'm Q1, I read a 0, I go to Q2, right? Then, upon reading the last 1, well, Q0, again, spawns 2 possibilities. But in Q2, you stay in Q2. So notice, upon reading the input, this one rejects, this one accepts. So we would say that this NFA accepts W, because at least one path or walk of the execution, as in one thread from the start of the execution, that is derived from the start, right? It accepts. Now, like I said previously, it could, as long as there exists one path or one walk from the beginning of the computation to the end that accepts, meaning that it has to end, if that is the case, then the whole thing ceases. It finishes. That means that these other threads don't matter in the sense that they could continue to execute if needed, but for an NFA, this won't be the case. So like I said, there's a bit of an asymmetry about this. So for example, and I encourage you to go through the same exercise with a different string for which this NFA would reject, and see that all the threads would have to be, all of them have to end for the rejection to occur here, right? It'd be no different than if I just picked off one of these and just followed a log, right? It's just, they would all end. So it doesn't matter, there's just a bad guess. So that's about the second intuition of this. So notice that the second intuition is quite literally this. So notice that every one of, if you look at this carefully, if you look at each of these vertically, you'll see that this actually tells you the set of states that the machine is currently in. However, if you take the parallel thread intuition to its most literal extreme, it would look like this. However, for some other computations, it could be that you may have multiple threads all in the same state, but like I said, it's computationally equivalent to just contracting all those duplicate state threads, all the threads at that state, to just being one of them. So that's the second intuition right here. It's just spawning more threads, right? So this is what I'm referring to as all these possible walks. Is notice that there's a walk here. This is a walk, but this one fails. This is a walk. This one succeeds. So since there exists at least one for which it succeeds, then the whole process has to succeed. If there exists no walks that succeed, then it rejects. So that's the second intuition. The first intuition is that what I'm saying is that if you can do perfect guessing, you have this clairvoyant ability to know that there exists this pathway. It's no different than if I imagine this machine, as it goes through this process, it might select the states that take me from here to there. Which is crazy, right? But the point I'm getting at is that, remember, all of these are on one transition. So please remember that. So this interpretation isn't crazy. It just doesn't make a whole lot of sense in the sense that we can't really tell the future like this, okay? At least as far as we're aware. But yeah, so this is a high-level view of how the NFA would compute such an input string for this NFA. So any questions at all? Any questions at all about this strange concept? It's a little strange if you've never heard of this concept before. Like I said, this is like magic, okay? So, and the reason why I'm saying that, again, just to reiterate, the machine is able to perfectly guess which thread of this execution it can reach to accept. And it means it makes a perfect guess of how you should follow along this execution. So you might view this as an execution tree, for example. So that's a very natural way of thinking about execution in a non-deterministic way, is you think of it like a tree as opposed to a single chain or path. So for those that are graph theorists or graph enthusiasts like me, you would view the deterministic manner for which execution occurs as a walk. The non-deterministic manner of computation operates more like a tree like this, specifically an out tree. But the point I'm getting at is, as long as there exists a walk in the tree that gets you to the accepting state upon reading the input, for an NFA to accept, that just has to be one. It doesn't matter if you imagine it like it's like literally exhausting all of these possibilities, or it just finds one. Some strange stuff, right? Some very strange stuff. Because remember, like I'm saying, if you wanted to simulate this process with an NFA, remember, it's you exhausting all of these, right? They're getting exhausted. That's pretty expensive to do. And the only reason why we can, for certain, do this is because there's a finite number of symbols that we read for the machine. There's other types of abstract machines for which this tree would actually be infinite in its size. So in those cases, you just can't do it, right? It's not possible. If somebody in the literature, some sci-pop pop book was telling you how somebody made a literal non-deterministic Turing machine or some other abstract machine like that, they told you I literally did it. I have a very strange feeling that that's probably not true. But I'm happy to look at anything somebody would send me, as long as it's merited with something of rigorous standing. But I'm just saying that that's usually a very skeptical thing to say. I'm not saying this is a hypothetical. This has literally happened. I've seen otherwise reputable publications do such things. I've also seen reputable journals even publish things that would say all sorts of weird things about complexity theory that aren't really that true. But that's because these topics are both fascinating, but also are easy to misunderstand. So that's why I make sure to go through this very carefully. So just to summarize what I'm trying to say about the computation of the NFA is that unlike a DFA's execution, if I were to walk through the same exercise I just did here, it would take the form of a directed walk, just a chain or path. Versus, in this case, it takes the form of a tree. So let's talk now about formal computation of NFAs. So I really want you to think carefully about this, because by no means is this I don't consider this an easy concept to first kind of play around with. It's a little weird. People aren't just used to thinking about machines that go into multiple states simultaneously and can spawn more computations. But the beautiful part is that all of this can be captured in quite beautifully with mathematics, the dreaded M word. And again, like I said, you can simulate an NFA. It's not magic. However, the concept of non-determinism is definitely a magical concept. On a broader scale. Not this whole very specialized circumstance here. Just going to drink a little bit of water here before we get to our next topic here. So depending on how far along we get today, what my plan is we're going to talk about the formal definition of computing for an NFA. So for an NFA. Then we're going to design some NFA. Well, NFAs, to be a bit more precise. Today's not my day, right? Just joking around. So once we have our formal definition, we design some. If we have time after that, I'm going to prove the correctness of an NFA that we previously explored during our design process. So that's our plan for today. If we don't get to the proof, we'll do it next time, okay? So let's get to this. So now that we've defined what an NFA is, or a non-deterministic finite automaton is, I want to define more formally what computation is on a non-deterministic finite automaton. Previously, we've seen a high-level view of how it works, and we talked previously about the concept of non-determinism and a couple different ways we could think about non-determinism. So let's give a formal definition. Formal definition of computing or computation. I'll say computing for a NFA. So just like with the DFAs, I can exactly define the computations of such a machine. Whoop, I don't want blue. Don't want blue. So blue back over here. Okay. So recall, NFA takes a state and input symbol and returns a set of states. Ooh, this marker's getting a little funky. Time to get rid of this one. There we go. It's gone. So similar to a DFA, we define an extended transition function. Transition function delta hat that takes as input a state, which you'd presume is like the state for which you're currently at. So if you want to perform the computations of the NFA, you would put the start state and then whatever string you want to process. Input a state and a string of input symbols. A string of input symbols. But instead, it returns a set of states. So remember, that's one clear difference between the DFA and the NFA. Is remember, the two things that characterize it differently was the transition function. It gives you a set of states. That means the extended transition function also has to have this property. But remember, non-determinism is a generalization of determinism. So it's going to have it where it's capable of being in more than one state at once. So we're going to define it now formally as follows in an inductive way. You can also think of this recursively, of course. So we're going to define delta hat as follows. So here's our basis. So this is what you do if you have an empty string. So delta hat, given a state q and the empty string, similar to just how we had it with the DFA, it stays at that state. It just stays at the state. So you'll notice that this looks exactly the same as the DFA's definition of the basis. Just get rid of these curly braces here. Because remember, it's a set of states now, not just a state. So when no symbols are read, the NFA remains in state Q. So that's the first part. Now, the other part is the inductive part of the definition. This is easily the most interesting part of today's lesson, is how this works. How exactly does the transition operate such that you could transition to a set of states to another set of states, which we've never seen that concept up to this point. So given string W, and again, we're going to use the same kind of decomposition as we did before. We're going to use the same decomposition where we're going to imagine this is all the string except for the last symbol. This is the last symbol. Where A is the last symbol. And X is the string W less A. So compute delta hat QX. So we're going to imagine we've computed this. Then follow any transition labeled A from this set of states. So it means that once you've computed this, in the transition diagram, you'll look at every one of those sets of states. And if you see a transition on A, you're going to follow with your finger on each one of those states and see where you end up being. So each of them one at a time, you'll just look at each one and see if it transitions on A to another state, if it does, and just tell me which set of states that it is in the result. So more formally, it means this. Formally, if delta hat QX is equal to a set of states P1 containing states P1, P2, all the way up to Pk, where there's k states in here, what you would do is delta hat of QW is going to be equal to the following. So remember, like I said, you're going to follow with your finger each of the transitions of the set of states on A. Some of them might die or get killed, quotation marks, but other ones may successfully find another set of states or just another state. So for each one of these, you would perform the transition function on that state given the symbol A, but you're going to do it over all of these. And you're going to put them all into the same bucket together without the duplicates. So you just go over all of these states, one after the other. You compute their transition function, and then you take the union of all of the states, the resulting states. So you just, like I said, for each one of those states, you're going to look at if there's a transition to another set of states. You're going to collect those up for each one of these states, put them all into the same bucket. That's a set of states. So the resulting set, that is what delta hat QW is. So this is how we can define computing for an NFA. So let's do an example. I think it'd be a good idea we do an example. So let's head over here. So as long as you remember the game plan, I just follow with my finger on each one of the states. Now keep in mind, I might need many fingers to make this work, so you have to be careful if you're doing it literally like that. It's more of that it's an imaginative finger for each one of the states. Because remember, it could be many, many states it could transition to depending on the size of your NFA and how many states it can transition into. We may not have, it might require more than 10 fingers, for example. So let's consider an example so we can kind of go through and use this. So I'm just trying to think here, which way would we like to go with this? I'm just trying to think here about which NFA would we like to play around with. I'm thinking we might use the same one. I'm tempted to use the same one. I'm just trying to think which one we would like to do. 11 point. Let's go with this one. 11.3. I got a lot of examples in front of me. Here, let's go with this. I'm going to use an example that will remind you of the one we just did previously. So I'm going to keep this over here. So I think it'd be wise I use the same diagram I used before. So I'm going to have three states, Q0, Q1, and Q2. And then next, I'm going to make a small modification to it. But let's let me just be careful here. I don't want to lead us in one direction where we're going to be thinking about things a little bit. Well, let's just go with the diagram we had previously. I think that's a pretty good idea. Let's go with the previous diagram. So let's consider our NFA M from our previous example. So in this example, we had it where it can be 0 or 1. We can stay in Q0. On a 1, it can go to Q1. On a 0, it can go to Q2. And then lastly, let's have it where on 1, it stays in Q2. So this was NFA M from our discussion about definition of NFA. So we had this NFA in particular. So we're going to process some strings using the definition of the extended transition function. So we're going to use the compute. My point I'm getting at is that we're going to compute this NFA with some strings, okay? So let's do this. So we're going to try some strings out on our NFA here using the extended transition function to describe the computation of the machine with that input. So let's consider some strings. So let's start off with W as follows. So let's consider, so for our first example, let's consider the string W is 0, 1, 1, 0, 1. Now, this is kind of like the one we had before. Either way, it's very similar, right? Actually, I think it is it the exact same one? I'm pretty sure it's the exact same one. Let's see here. It is, it is. So for our next example, we're going to be just considering the same string we had from when I showed you a high-level version of computing for this NFA. So I'm going to show you how we use this formal definition in this case. Then we'll see another string just to see how this works with different strings. Because I want to go a little careful with this. Okay, so delta hat, so we're going to be building up to the string one symbol at a time. So we're going to start off with delta hat Q0 on the empty string. Well, what is that? What is that? Well, the basis was that it's Q0, right? Because I haven't read anything, so it stays in this set of states. Now, let's consider when we read the first symbol, delta hat Q0, 0. So we're going to read the first symbol. Well, what does it mean? Well, we take each one of these states in here. I apply the transition function on whatever the symbol is. The symbol in question is the symbol I'm currently reading, right? So I read a 0, so it means that whatever delta hat of this would be was this, where I apply the transition function to each one of the symbols, not symbols, I apply it to each one of the states in here. Sorry, I'm getting really excited here. I'm getting so excited that today is just a wild one. There's a lot on Dan's mind today. So anyways, I have, when I take the empty string, I end up with Q0. So what to define and compute, to compute on this symbol, I read 0. To do that, I'm going to now consider each state in this set. I'm going to apply the transition function. I'm going to apply a union across all of these, okay? So here I just have 1, so it's really easy. So it's just Q0 on 0. So Q0 on 0, okay, it just says, I'm supposed to just stay in Q0. Nothing too interesting, right? Okay, we got delta hat of, now we're going to read the 1. So Q0, 0, 1. So next, we have Q0. So remember, it's just one state here. So I just do the same thing, except now I'm going to try it with 1. Remember, that's the one we're considering here. So I have 1. So I have Q0, 1. So on 1, it stays in Q0, but it also goes to Q1 at the same time. So it's Q0, Q1. So now notice now I have 2 states. Let's compute delta hat Q0 of 0, 1, 1. So, because that's the next symbol we're reading. Well, what does this say? It says, whatever the result of applying delta hat to 0, 1, I'm going to take each one of those states. I'm going to apply the transition function on the symbol 1. So this will be delta Q0, 1, union delta Q1, right? Because that's the other state. I go through each one of these and I applied the transition function with that symbol, that one I'm reading. Well, Q0 on 1. Q0 on 1 is just Q0, Q1, right? However, in Q1, if I read a 1, notice there's no transition out or in Q1 on symbol 1. So that one, it gets killed. Hence, that's nothing. It's an empty set. And that means that the result of the union operation here is just the states I'm left with are Q0, Q1. Let's consider the next symbol. Delta hat Q0, 0, 1, 1, 0. Okay, so it means I'm going to apply now the transition function to Q0 and then Q1 on symbol 0. Q0 on 0. Union delta Q1 on 0. Well, on 0, Q0, it stays in Q0, right? Upon reading 0. How about here? On 1, on Q1, reading is 0, it goes to Q2, right? But only Q2. So we end up with Q0, Q2. So now we have Q0, Q2. Let's read the last symbol. So 0, 1, 1, 0, 1. So now, over that set of states, I'm going to read 1. So Q0, 1. And whatever the result of the transition function for Q2 on reading 1. We're going to take these, lump them together, okay? So Q0, 1. So remember, it's a set of states. So if we have duplicates, we just discard them, right? Like, it doesn't matter. It's a set, not a multi-set. So on 1, Q0 gets Q0, Q1. Right? However, on Q2, when it reads a 1, it stays in Q2. So notice that the result will be Q0, Q1, Q2. So please note that Q2 is an accepting state, or final state, so it accepts. Do you see that? And in fact, what I want you to do is, in our previous lesson, we've seen a high-level version of how this is being carried out. I want you to look at the result from each one of these as soon as I read the first symbol. Take a look at what the sets look like and read the columns of states, and you'll see that they match up exactly with these ones. Fascinating stuff, right? So, there is no weird, funky business happening here. It's all just a bunch of union operations on transitions, where now we have sets of states, and the union operations take care of what happens when we have multiple states to deal with. So let's do another example. I'm going to include another example in here that has it where you have 3 elements in a set of current states, but I'll include one now that is it's slightly different. Let's consider when the string W is just 1, 1, 1. So it's just 3 ones. Let's consider this scenario. So let's go through the same process. I'm going to start off with the base case of the definition. Q0 on the empty string. Well, this should just be Q0, right? We haven't read anything. Now, let's read the first symbol. So on 1, we're going to apply the transition function. Q0 on 1. On 1, notice it can be Q0, Q1, right? Now, let's read the next symbol. So remember, I'm going to read now the 1 at the end of this string, because everything else has been computed. I have Q0, Q1, so I'm going to apply the transition function on each of these, take the result, and union each, okay? So I'm going to take the result of each and put them all together in one bucket. So I have Q0, 1, union delta Q1, 1. And naturally, what happens? Okay, in the first case, Q0, 1. We get Q0, 1 again. Union on a 1 in Q1. We get the empty set. There are no set of states other than the empty set of states in that case. So we end up with Q0, Q1. And now we have to read the last symbol. Delta hat, Q0, 1, 1, 1. So we're going to apply the transition function on Q0 and Q1 each. On a 1 again. So delta Q01 union delta Q1, 1. This should look awfully familiar to you. And there's an actual really nice property that's happening here, by the way, with why we put this loop here at the beginning, the self loop. But notice here that, again, we'll get Q0, Q1, union, the empty set, which ends up being, again, Q0, Q1. Now I have a question for you. Does it accept or reject the string? Does it accept or does it reject? Accept or reject. Are any of these states the final state that in our NFA? Remember, we only have one. We have Q2. None of them are, right? None of these are. So none of the states are, so there's none of these are in F. So in this case, we would reject, right? So again, there's going to be another example here in the notes. But now I want to define what the language of an NFA is. Because before we had a definition for the language of a DFA, now we would like to have a definition using our formal definition of computation. I'm getting really excited here. Of an NFA. So we got a language of an NFA. So given an NFA M, we're going to define the language of M, L of M, to be equal to all strings W such that delta hat Q0 on string W. So remember, this is defined for M. So what happened in our previous example? We looked at the set of states and we didn't see the final state upon reading the input string, right? So there seems to be something really important about having at least one of the states being in F. So whatever the result of this is, one of these has to belong to F. So one way I can write this out is I take the intersection with F, and if there's any ones in common between these two sets of states, then this resulting set will be what? Non-empty. It'll be non-empty. Meaning there's at least one state that's in common between these two sets. That's what the intersection would give me if it accepts. So any set of strings that follows this would be called the language of this NFA. So as long as when I'm done reading the string W with my NFA, if in the result has one of its states being in F, keep in mind it could be more than one, we would say that it accepts. Hence it belongs to this language. So just to kind of bring this all together, if we think about this in terms of the guessing process that we had when we talked about perfect guessing, is that the whole idea here is that if I give you a set of a string W, there exists a sequence of choices that leads to the final state. However, in that case, if it rejects, it means that there is no chain of guesses that will get me, or good guesses, that will get me to the final state. They're all just going to be bad guesses. So there's no way to accept W in that case. So this is the formal computational definition. This is our definition for computing for an NFA. Pretty neat stuff, right? Any questions? Any questions at all? Any questions about the definition for computing on an NFA? let's head back over here. But if you have any questions, just put them in the chat. I'm very happy to answer any questions. So let's boogie on down. We're going to design some NFA next. Oh, sorry, NFAs. I'm just having a weird day today. Miss Kitty sort of hexed me a little earlier. If you weren't here at the beginning, Miss Kitty just decided to just crash our lecture. It was a thing of art, okay? But what we're going to be doing next, I'm just going to get my notes here in order. Yeah. Let's... Just going to drink a little bit of water. But if you have any questions, just put them in the chat. Okay. Well, let's move to our next part here. Next, we're going to be talking about designing NFAs. So next, we're going to design some NFAs. So we're going to use a lot of the intuitions that we built up to this point to help us do this process. Now, I must stress that we haven't really talked about proving the correctness of NFAs. So in this part, we will not talk about proving their correctness. Instead, I'm going to motivate why they would be correct. But after, I'll give you some ideas of how we might go about that. So let's talk about designing NFAs, or Nondeterministic Finite Automata. Let me just get a different marker. This one sort of deceived me. Out of here. It's gone. It's gone, everybody. So, let's try a different marker. So before we get into designing some specific NFAs, I thought I would show you a technique. So a technique that you couldn't do with a DFA, at least in this exact way. I don't want to say too many things. Is that there's a technique that we can use for designing NFAs. I like to think about it as being producing more guesses. So this is a helpful technique we can use to exploit non-determinism. So let's consider the following NFA. Yeah, geez, it'll look a little funky, I know, right? Consider the following NFA. So it's going to be similar to the one we had in one of our earlier examples. It's going to have 3 states. Going to have 3 states. Q2 is going to be the final state. I'm just going to get rid of the loop on Q2. Otherwise, it's the exact same as our previous NFA in our previous lesson. So, if I have 3 states like this, notice that if I get to Q2, if I read any more symbols after that, I'm toast, right? That thread is done. So, a common technique that you can use with NFAs is that you can use self-loops akin to the one I have here on Q0 to produce more guesses. Another way of looking at this is thinking about it as spawning another thread, for which if one thread fails, it gets killed, you can use another guess to spawn another thread, for which it might successfully reach Q2 upon reading the input. So notice that state Q0 can be used to transition always. And the intuition here is that keeping a thread, if we're thinking about this in terms of parallel threads, keeping a thread alive. Now, if you're wondering why this matters, is that you can imagine, upon making a certain set of guesses, akin to the first intuition I gave you about perfect guessing, is imagine you want to have the guess that actually gets you to Q2 and accepts if it exists. If, for example, I haven't read enough of the input to get me here, I want to make sure that I supply another opportunity for a walk to occur in terms of execution from wherever the failing point could be to the final state, or a final state. So in this case, you could imagine it like I'm just keep allowing us to keep allowing a binary string to occur over here. Meaning that ever I run into a situation for which I start reading a 1, I can have one of the states goes to Q1, and then it reads a 0, it can go, that thread can go over to Q2. However, if, for example, I read another symbol, I could still have one sitting over here if there was another 1 read to go back over here and try it again. Do you see what I mean? So it allows you to produce more guesses. This is a nice technique you can use when you're designing NFAs. So I have a question for you, by the way. What language does this NFA accept then? So think about it very carefully. I thought I would start off with this one because it's similar to one of the ones we've seen before. So if you think about it intuitively, remember, like I said, it keeps allowing us to take in a 0 or a 1, and it stays in Q0. And if ever it sees a 1, it allows it to be in Q0 and Q1 at the same time. But notice that as soon as it reads any more symbols after this, it's done. It won't be able to do anything over here, but you're still alive over there, right? That's something you can always guarantee when you look at this. So if you're not convinced by this, try an input string and notice that every stage of the computation, one of the states is always going to be Q0. So that means that you can think of this like I keep allowing you to generate another binary string to try out getting the Q2, but not overpassing it. Almost like we're playing a little bit of I'm not sure if you've ever seen these at the arcade or something like that, or played a game where you throw a ball into a hole and you get just about there, but you imagine if you had the ability to get it so it goes in the hole, but every single time you make a mistake, just before you make the mistake, you're allowed to revert your operations and try it again while you're in the process of making that mistake. Weird stuff, right? But the point is what does this guy do? Is this NFA, so this NFA accepts all binary strings that do what? So remember, if it reads a 1, then a 0, then it reads anything else, it's done. It won't, as in it will kill that thread. However, if you read the whole input and after reading a 1 and then a 0, and you're here, you accept. Well, it means that that string has to end with 1, then 0, right? So accepts all binary strings that end with 1, 0. So this is our first example of an NFA here. Notice here, the whole trick here is just to allow us to keep producing guesses. If ever we make a mistake, we get another go at it. It's a very, very generous NFA. Gives us many tries as we need while we're still reading the input. So there's still a fixed number of attempts that you can have, right? You can't keep trying forever. that's because we have only a finite length of input. So let's do another example. So we're going to try designing, because remember, previously we had seen that DFAs were capable of detecting fixed length substrings. Likewise, it was also able to count occurrences of some constant size of, say, a certain symbol in the string. Likewise, we also even seen how this would work if we're talking about the parity of how many like ones or zeros appear in a string. In that case, we've seen the number of zeros if it was an odd number. Let's see if we could do something like this in a couple other different settings, but with an NFA. But you'll notice quite quickly that the NFA gives you a lot of flexibility when it comes to making oopsies, okay? Like I said, it allows us to have another go around. So let us design an NFA that accepts all binary strings where the third last position of the string is a 0. So just to clarify what I mean by this, let's consider a couple of example strings. So just as a quick example, 1 1 0 0 1 1. So this is the last position. This is the second last position. This is the third last position. There's a 0 in here, so it should accept this string. How about 1 0 1 0 0 0? That's the last position. Second last position. Third last. It's a 0. So accept. How about this one? 1. Let's do something fun here. Let's go 0 0. Should it accept this string? Yes or no? Which one, should it accept or reject 0 0? Well, it doesn't have a third last position at all, so you should reject it. There's simply not enough symbols in that case. How about 0 1 0 0? Well, this certainly has enough symbols in it. Well, let's look. Last position, second last position, third last position is a 1. No, we should reject that one. So let's pick up the idea we had about producing more guesses to help us design an NFA in this case. Well, let's start off with what we had before in our previous example. We know how to make it so it ends with a certain target string. But we don't really care about everything else except for the fact that the third last position is a 0. So let's use a technique that we used with DFAs, but we're going to combine that with the idea we had about producing more guesses. So the first natural place for us to start is consider all input symbols on a state called Q0. This will allow us, if ever we fail to get a pattern for which we encounter a 0, because remember, the third last position has to be a 0. Then anything else that follows, as long as there's 2 more symbols, whether they're 0 or 1, we're okay, right? But suppose that we fail to meet that pattern, because remember, the pattern looks like this. So it's any number of 0s and 1s, then you see a 0, and then you have a 0 or a 1 and a 0 or a 1, right? But anything after that, not allowed, not allowed. That's the form of a string that gets accepted. So this will allow us to keep this part. So we can keep this part as long as we have this, because this will allow us to keep producing guesses. So next, we need to allow it to see the 0. Then, akin to when we were trying to detect a substring, we're going to have a pathway that permits us to read the last couple of symbols. But now, because we're allowed to have it, keep in mind, this thing is allowed to be in multiple states. However, at this stage, if you get to Q1, as long as you read either a 0 or a 1, we're okay, right? As long as you read a 0 or 1, you're okay. So I'm going to make Q3 the final state. So there's just one final state, just Q3. And bam, there we go. So notice that this will allow us to read the first part of the string, 0. Then we have 2 spots here. How about if I wanted to ensure there was, like, if I wanted to allow the, like, because this is one thing you have to be very careful about. What would happen if I put a self loop over here that had 0 and 1 in it? What would happen? Well, now you have to be a bit careful, because if it successfully sees a 0, we've just essentially just allowed it, as long as there exists a 0 or 1, or a 0 or 1, as long as it only has that form, any other string works, right? So if ever I wanted to just have it where it's a string, where it's a 0, then another 0 or 1, then another 0 or 1, this will work to satisfy such a requirement, right? But that's not what I want, right? I need to get the specific target form. So do you see how with an NFA, if I want to detect a substring or a pattern, this idea that we had before where we kind of come up with a pathway works quite nicely. Again, just now we can take advantage of the non-determinism to keep spawning more threads or more guesses. So if ever we botch it, we have another go around until we've finished reading the string. But yeah, so that's another example there. Let's take that idea now, let's extend it even further. I must stress that you can do a lot of other things with NFAs. For example, you could generalize, like you could take 2 DFAs and you just be like, yeah, I want it to do this or this. You can take that and do that with an NFA. But we'll talk more about that when we explore other NFAs in the future. There's another natural way of doing that, but let's consider one last example here. So let's consider when we have an alphabet with 3 symbols in it, C, A, and T, cat. Like Miss Kitty. She's a cat. So suppose I have a cat. We're going to, so let us design NFA that accepts any string. And when I say any string, I'm referring to any string over this alphabet. Any string that includes cat, so the phrase cat, or tack, which is it backwards. So let's take all of the ideas we've seen up to this point for designing NFA. Let's try approaching this. Well, let's think about it. Let's start off with a start state of Q0. Now, notice that now we have 2 possible patterns to look for. And remember, like I said before, if I want to make more guesses, I can just include a self loop to help me ensure that at least one thread stays alive. So I'm going to do this over all of the input symbols, or our alphabet here, so that if ever I botch finding one of these patterns, we're still okay. So let's consider tack first. So if I want to detect tack, does anybody have any ideas of how I would detect tack? Well, I know tack would look like this, right? We've seen this technique before when we were studying DFAs, right? Where I would just have a pattern that's encoded in the pathway like this. right? This should cut it, right? Actually, yeah, I'll refer to them like this. However, it says that it accepts any string that includes tack. So keep in mind, as long as tack appears in the string, we're okay, right? However, this means that tack would be at the end of the string. We need to allow, akin to our previous discussion, we need to allow it to read more symbols, any symbols. And so far now we have it where it will detect if the word tack appears in, or phrase, or key phrase, appears in the input string. How about cat? What can I do with this machine now? What can I do? Well, it's very nice because notice that if remember, it's cat or tack. It doesn't have to have cat and tack in it. Just cat or tack. So notice quite quickly that, okay, well, that means I can make another pathway. Or I can have, say, Q4, Q5, and send it over to Q3 again. Like this. So can you see how I can easily generalize this if I wanted to put more key phrases? So this is one versatility that you get with an NFA. So it gives you a lot of choice, design choice over this by the fact that we can keep spawning more guesses, right? If ever we botch it. So we have opportunity to botch reading the string to get that perfect guess. Now remember, in an NFA, the intuition is that if it can reach here, that it can and it will follow that path of execution. However, when you're designing and thinking about it, you might want to think about kind of like what I just described before. So notice here now, I can allow there to be as many symbols as I like at the beginning. Because remember, as long as Q0 stays alive, if we botch detecting one of these two patterns, and we don't get over here yet, this will allow us to make another opportunity to try it out. As long as it appears in the string, we're okay. So this is actually how you can design an NFA that does such a thing. So are there any questions? Any questions at all? So I thought I'd show you a few examples of designing some NFAs. So a part of me wants to just assume that A stands for automata, even though it's automaton. It's just because my brain is just being a little silly today. Are there any questions about designing NFAs? Or you have general questions about nondeterminism or anything like that? Happy to answer any questions. This is I consider it a very neat concept. It's a neat idea about computation. So this is another way you can think about computing. It's just a very strange and abstract one, yes. At least at first. I think that when you get a little bit of a grip over it, it's not as scary looking. It's just not something you really can conceive of in a deterministic way, hence its name. So it's more of that you could simulate it, but this idea of having literally multiple states at the same time, it's more of that you're simulating the idea because we don't have this idea of future telling like this. At least a perfect way of doing that. Okay. We're going to be moving into our last part of our lesson here today. What I want to do is I want to talk about proving the correctness of a NFA. Since we talked already about DFAs, this is actually going to go a lot faster than I did with the DFAs. The main reason why is because the technique isn't any different. It's just that I'm applying it now to an NFA. So that means that we're just going to pick up the definition of computing for an NFA. But the big trick here is that I can't just simply exhaust the input symbol with a state with a lot of cases. Instead, it turns into a different game. Instead, it turns into, okay, if I do get to this state, it says it's supposed to have a certain behavior. How did I get there? And that's going to come back to how I define the extended transition function to you. So again, it ultimately boils down to the definition of computing, just like when we talk about an algorithm, just more broadly, it's about like what the algorithm actually does, okay? You have to study the algorithm first before you can prove anything about it. But the thing that we have as a benefit at this concrete level is I can tell you exactly how the computation plays out in an exact specified way by a function. So, I got the hat. Just gonna drink a little bit of water here. I'm a little thirsty today. Miss Kitty just took it out of me earlier. Okay, so let's see here. It's been a little bit of a wild couple of days here on my end. Just reading the news and stuff. There's a lot of concerns around academic freedom these days, and I've been looking into a lot of these matters. Anyways, let's move on to our next point of discussion. I'm looking forward to talking to you about this. Yeah. Okay. So next we're going to be talking about the correctness, and specifically proving the correctness of NFA. Sorry, today is just a wild day. I had this lecture all set up, and then Miss Kitty sort of just showed up in the morning and just started messing with me. So let's. The other thing is I'm just having a little bit of fun here with you. So if you're watching this in the future, if you're wondering what's going on, it's because I'm having a little bit of fun with everybody. Okay. So anyways, let's get to the point here. So let's get down to business. So we're going to talk about proving the correctness of NFAs. So previously we had seen how we can prove the correctness of a DFA. And we've seen some techniques there. Namely, we've seen the concept of state invariance. We're going to use the same idea here. And the exact same game plan. It's just now instead we're using a different computational definition. So our extended transition function is a little different. So that means that the way we use it will differ from when we did it and try to prove claims with the DFA. In a DFA, we just tried to exhaust all possibilities over some so-called state invariance, and then we just tried them all, unless we wanted to be a bit more clever about it, which is okay, but well, certainly you could do this. It can be a little time-consuming, but it's straightforward, and how would you combine it with induction. So previously we talked about a DFA and how we could prove correctness there. I just want to summarize how the game plan would change a little bit here with NFAs. So we need to ensure that for every input, so for every input W, in the language of our NFA M, it has to be that W's in this language, as we defined, remember this means that W is accepted by the NFA. If and only if, I'll abbreviate if and only if with IFF, the W is in the language we want M to recognize. That's kind of the overall game plan. So this is our game plan. So that is, if I call this language L, that is, a W is in L if and only if W is in L of M. Remember, L of M is the language of the machine. This is just the desired language I would like to prove. They're not the same thing. Sometimes, well, the goal is to prove that they are the same. But the thing is, we may not necessarily have that. In that case, you would have an incorrect NFA. So, we're going to be adopting a similar framework to before. We're going to be trying to use state invariance again. But as I stressed in that lesson when we were talking about DFAs, you don't have to use state invariance. If your DFA has a very specialized structure, just like an NFA may have a very specialized structure, it may require just proving maybe one invariant as opposed to using a state invariance over all of the states. You might not need over all of the states. You just need maybe just one or two potentially, or just, it depends heavily on the NFA or DFA in question. So similar to with DFAs, suppose we want to prove NFA M and language L satisfy L of M is equal to L. Remember, L is the language, L of M is the language of that machine over there. In this framework, you would employ an argument just like this one. Employ the following argument. So the first thing we do is we identify state invariance. So this would be how you would prove the claim, or at least the main part of the claim. So identify state invariance. So, just be clear what I mean by this. For every state Q in the state of the set of Q's, we're going to determine some language LQ such that when M transitions into state Q upon reading string W, W is in LQ. Specifically, what I'm saying is that W is in LQ if and only if the state Q is in the extended transition function. It's in the set of states resulting from computing the extended transition function on Q0 W. So upon computing the string on W, if it's in, sorry, this should be Q, not Q0. It should be Q. When I actually no, fine. Q is, yeah, it is Q0. It's Q0. My apologies. Yeah, what matters is that Q is in the set of states upon processing W. So this if and only if has to exist. So you do this for each one of the states. That's the first step. So that's the hardest, I would argue that's probably the hardest step, is identifying those. The rest of it is a little bit more of the busy work, okay? But you have to check, okay? Is now you got to actually prove the state invariance. So the way you design your NFA will play a big role on how you identify the state invariance. So a part of this process of proving the correctness of the NFA may play a role in how you design the NFA too. You might want to design the NFA so it's easy to prove that the NFA is correct, and then work your way from there. So prove the state invariance. So using induction. So you're going to perform mathematical induction on the length of the string. So on the length of W. Prove for all input strings W. For all input strings W, and every state Q in Q. What you want to do is you want to prove that Q is in delta hat, the resulting states of delta hat. Remember, there's a hat here. It's not just a transition. It's the extended transition function of Q0W. So just upon processing the string starting at Q0 on string W, if and only if W is in LQ, as I previously stated. But you'll prove this using mathematical induction. So you go through each one of the states, and you just simply argue that that is in fact the case. So depending on how complicated the transition function is, it may change how you might go about it. I'm going to show you in my example a variety of different ways of going about it. But I must stress that if you think carefully enough, there might be other ways of going about it, as long as you understand how to prove an if and only if claim. So the point is we work with some logically equivalent statements, or we might try to prove it using two-directional proofs. So I might try to prove if given this, that this, if given that, then prove this. That's another way you might want to work with this if a state invariance is a little bit more complicated. And lastly, you just use the definition of L of M. Right? Remember, the definition says that whatever the result is from Q0 upon reading string W, intersect the set of final states. As long as that isn't empty, it accepts, right? So all you do is you look at the set of final states, and you look at all those languages, the ones like these LQs, just look at the ones for the final states. Take those together, and boom, there you go. So prove that the desired language L is actually going to be equal to the union over all of the final states for L of Q. And that's the way you could use state invariance in the context of NFAs. But I must warn you, one detail I must warn you about is that when you're considering state invariance here, remember we have to keep in mind the definition of computing for an NFA. Remember, the game in town with the DFA is that I know given a state, a symbol, I know which state it's going to go to. However, here, if I go to some state, I may have gotten there through several other means. So that's what's going to make the proof of correctness with an NFA be quite a bit different sometimes than with a DFA. In a DFA, it's quite natural to exhaust all possibilities. But with an NFA, it may be the case that sometimes it may be a little tricky to do that. So you have to be very careful when you're arguing claims about the state invariance. So to carry out our example here, I'm going to use a previous example we had when we were designing NFAs. So I'm going to show you that one of the NFAs we presented is in fact correct. And we're going to do that using mathematical induction and the technique of state invariance. So we're going to use state invariance, we're going to cook up some state invariance, we're going to prove those state invariance, then observe that one of them actually tells us exactly which language the NFA recognizes. And then we're done. I make it sound so easy, don't I? But the thing is, once you understand the main idea of this technique, this argument, it's not too scary. It's just that you need to think very carefully about it. Not everything in this world is easy to just cook up out of the blue. You have to sometimes just sit there and stare at things for a while and really play around with the ideas you have in front of you, which is always something that somebody like myself does when I do research. It's not unusual to sit in front of a board for hours on end trying to figure out something. That's something that's perfectly fine to happen. And when you're first studying theory of computation, same thing happens, okay? So let's consider this example. So I presented this NFA. I was about to say DFA, but let's consider this NFA. Recall this is the one that I gave you that detects if the string ends with 1, then a 0. So remember, the claim here was that this NFA, it detects binary strings which end with 1, then 0. So we're going to prove that it is indeed the case. But what I want you to really think about is state invariance. So let's think about some state invariance for this. So let's think about this. What can we say about Q0, Q1, and Q2? If I have a string, so upon reading a string W, if I end up in Q1, or end up in Q2, or end up in Q0, what can I say about the string? Now, one thing that's going to make this feel a little different than with the DFAs is that here, it may be the case that not every string will map up to exactly one of the cases. That is a feature of nondeterminism that we would like to exploit in our design sometimes. So, what can I say about Q0? I alluded to this when we were designing this NFA. Is notice that no matter if you read a 0 or a 1, it always, if you look at the states of the NFA, Q0 is always in there. So we can carefully characterize this. So Q0 is in delta hat Q0W, if and only if what? W is a binary string, right? But you can even go even further and literally just say that Q0 is in here at all stages of the execution. But I'll just state it like this. So if W is a binary string, it has to be that Q0 is in here. that is most certainly a fine state invariant. So with NFAs, if you have it where you have this approach where we try to keep making guesses, producing more guesses like this is not something very surprising. How about Q1? What can I say about strings W? So if I give you a string and you end up in Q1, what can I say about that binary string? What can I say about it? Well, let's think about it. How did I get to Q1? Observe, and this is something that will come up in our proof, is observe that the only transition into Q1, or even to remain in Q1, is from Q0, and it's over this symbol. What's the symbol? 1. It's just 1. So that means that the string has to end with a 1. So Q1 is in delta hat Q0W if and only if W ends with a 1, or ends with 1. So if it ends with a 1, the claim is that it will be one of the set of states. Finally, Q2. Well, this should match up if we are correct. And Q2 is the final state. We sort of gave away what Q2 should be then. W has to end with 1, 0. So W ends with 1, 0. These seem like perfectly reasonable state invariants, right? If we can establish these state invariants, notice that Q2 is the final state. Hence, that's all we need to prove the correctness of the NFA. However, as I explained previously when we were talking about state invariance, sometimes it's very difficult to know because all we have at our disposal are the set of states that we currently are in. I don't know how it got into that state up to that point, except for it may have been for some other reason. It may have been because, hey, look, I was in Q1, I got to Q2. Why did I get to Q2? I read the 0 here, right? It's pretty straightforward. However, it could be the case that I read a 1, but I was in Q0, but I could have stayed in Q0, but I could be in Q1 as well. So a very similar thing happens as well with NFAs. So it's a good idea we carefully go through and see what happens in each case, on each transition, namely. So this is what we're going to prove. This is the primary claim. Once we have that, we just look at this row right here, and that will give us the correctness based on using our argument for state invariance. So here's our lemma. So we're going to prove this lemma. And once we have that, we just have that one piece of the argument to get the correctness. So given NFA M, but I'll refer to this just in our proof as M end, just to keep it simple for us. NFA M end and W, which is some binary string. It has to be, this is true for M. So upon processing string W, if you're in Q0, it has to satisfy this. Q1 satisfies this. Q2 satisfies that. That's the claim. We're going to prove this using mathematical induction. So please, if ever we need to go over here, just keep in mind this transition diagram. So to prove the claim, we use mathematical induction. Mathematical induction on the length of the string W. So what's the first thing we do in an induction proof? The base step, right? So we're going to start off with the length of the string is 0. Since the length of the string is 0, there's only one string with length 0, right? The empty string. So let's just see what happens when we're given the empty string. We'll use the definition, the basis of computing's definition on an NFA. I know it sounds a little bit weird, but go with it, okay? So let's consider the definition of computation for an NFA when we're given an empty string. Well, we stay in the same state, right? So let's see what happens. So in this case, W is equal to the empty string, and by definition, it has to be that delta hat Q0 W is equal to the set that contains only Q0. So remember that the string W, it's a binary string, right? It just has no symbols. String W is, in fact, it belongs to the set of all binary strings, right? So what can we say? Well, it's saying Q0 is one of the states that you get, so, and it is a binary string, so we're okay there, right? So the first invariant, I'm just going to number these invariants. So the first invariant, so 1 holds. So 1 holds. How about 2 and 3? Because remember, all 3 of these have to hold. And remember, it's an if and only if claim. So logically speaking, if Q1 isn't in here, then it has to be that W does not have this property, right? Likewise here. If Q2 is not in here, then that means that W doesn't end with a 1, 0. So, well, let's see. The empty string most certainly doesn't end with a 1, right? So we're okay here. And it doesn't end with 1, 0, so we're okay here too, right? So let's just say that. As epsilon, the empty string, does not end with 1 or 0, and the set of states does not include Q1 or Q2. I'll just say 2 and 3 hold. Hence, the statement is true. Statement referring to the lemma. The statement is true for all strings of length 0. So it's true when W has length 0. So now we've completed the base step. Now we got to get to the induction step. Now, if you aren't just like, okay, I want to check some more cases, you're welcome to go check when the length is 1 and the length is 2, but you'll find that my argument here works regardless. So you might be compelled to do something like that, and keep in mind, for some NFAs that might make things easier, or it depends on your argument. But notice that the only strings that get accepted here are going to have length 2 or more, right? So that might be helpful depending on what kind of argument you're trying to impose here. But I'm trying to use a little bit of a broader argument here that requires me to just check things a little bit more carefully by using a stronger induction hypothesis. So just please keep that in mind. So just don't think that you just have to prove this case. You could go up higher if needed for your induction hypothesis, okay? Well, now let's consider the induction step. We're going to fix some n greater or equal to 0, right? Because we proved it up to and including 0, right? So I'm going to go up 1 notch. Let the length of the string W equal n plus 1, assuming, so this is really important, this is the induction hypothesis, assuming the statement for all strings of length n holds. So that's the induction hypothesis. So we're going to show how to prove the claim for all strings of length n plus 1 that follows from the induction hypothesis. So let's check this out. So consider W, and remember this is an arbitrary string, W equal to XA. So we're going to use a very similar setup that we did with the DFAs. So I'm going to have all of the symbols just before the last symbol. The last symbol is A. What can you say about X, by the way? What's the length of string X? What's the length of the string? If this is whole thing's length is n plus 1, the length of X is what? It's n, right? So we're going to use that fact to help us here. So, where A is the final symbol in W, presuming that X is everything but the last symbol. Now we prove that the statement, the lemma, that the statement also follows. So So remember, we need to use the induction hypothesis here. That's a key part of the induction step. We have to show, when I give you n, I'm going to show you where it follows that if n was true for all strings of length n, it has to follow for all strings of length n plus 1. But the statement also follows for string w. Now, as I alluded to, what's the first thing you might try doing here? We've got the setup. What should we do? Any suggestions? Any suggestions at all? Well, I alluded to this. Look over there. What can I say about this? So remember, w is equal to xa. This is one symbol. How many symbols are here? N. There's n symbols there. So x has length n. So I'm going to use the induction hypothesis. I'm going to apply it to x. Then all I have to do is put the cherry on top by seeing what happens when I deal with a. So string x has length n. So by the induction hypothesis or inductive hypothesis, we could say the following. First, that Q0 is in delta hat Q0 x. So upon processing x, starting at Q0 with this NFA, it's in Q0 if and only if x is a binary string. Unsurprising, I know. It's amazing. 2, Q1 is in delta hat Q0x. So upon processing x, it's in Q. Q1 is one of the states if and only if x ends with a 1. And lastly, state Q2 is among the set of states upon reading x if and only if x ends with 1, 0. So now we have this with x. We're going to try doing something similar to what we did with our DFAs. So I'm getting really excited. So let's get into this goody juice, okay? I'm going to keep the NFA on the board, but I need you to remember these invariants because we're going to use them. Because we're going to keep this NFA up on the board because it'll be helpful for when we're proving the claims. So just remember the lemma. The lemma is going to be that, except it's string w. Any w. So once we get the induction step in place, we can then use the principle of mathematical induction and complete the proof. So now that we have this, we prove each state invariant holds for w separately. Now, one telltale sign you're working with something slightly different is remember that when I did this with the DFA, the last symbol, it either was usually a 0 or a 1 if we're working with a binary alphabet. So I had only like 2 choices. So if it was in state Q0, Q1, or Q2, I would have at most 6 cases where I would check what happens when it processes X and it's in a state, and then I look at what A is. I would do that for each one. There's a bit of an issue when doing this with an NFA, is as previously described, it could be the case that there's a reason how X contained a certain state. But remember, they may contain other states too. Likewise, there has to be a reason why that state was included as part of the set of states. So instead of working with X, where I break down the cases on X, I'm going to break the cases on W. So I'm going to directly have it where I'm going to have 3 main cases, one for each of the state invariants where I consider all strings of length n+1, and I'm going to use in each case those guys over there. But I need to the best way I can describe this to you is I'm going to reverse engineer how X got there. And I'm going to use, I need to carefully ensure I can use these cases that I have here to ensure that I can derive what happened up to that point. So watch this carefully. It's almost like reverse engineering how I got there. And use properties about the NFA to tell me how I can only get there by a certain means. So let's start with proving the first invariant. So let's go. So let's consider state invariant for Q0. So this one's going to be not as interesting. String X was already a binary string, right? I didn't say that state invariants have to be these very ingenious things, okay? So, and it also has to be the case that W is also a binary string, right? There's nothing impressive about this statement because A is either 0 or 1, right? So if X is already a binary string, then W also has to be. That establishes one side of the invariant, right? So since I already know that X is already a binary string, then I can say what's going on at Q0, right? Because X, by the first invariant, would be here, right? Because it's a binary string, regardless of what W is. So, state Q0 is in delta hat Q0X. So upon processing X, by the first invariant, and I must stress this is on X. So I'm applying what we have over there. So state Q0 is in delta Q0A. So I'm applying the transition function on Q0 given A. And 1, so the first invariant remains satisfied for W. So please note that the way I was able to invoke this right here was because I knew X was a binary string, right? And because of that, I could say, okay, well, look, I could just use the first one over there on X, and then I just look at the transition function. Okay, Q0 on A, regardless if it's 0 or 1, Q0 is in this set, so that means it's still in, so Q0 is still in the set when I apply it on W. So that proves the first invariant for all strings of length n+1 for the induction step. Remember, we're just trying to show that going from n to n+1, we're trying to use the induction hypothesis from all strings of length n to get to the next symbol. So that was one of the easy cases. So let's consider the state invariant for Q1. So the state invariant for Q1, remember, that means that upon reading string W, I have to have it where the string ends with a 1. So string W ends with a 1. It means it's right here for one of the states. So it means Q1 is in the set of active states upon reading W. But how do I get to Q1? How do I get to Q1? How do I get here? Let me put my Explorer hat on for my very unexciting adventure, okay? Why do I say that? The only way I could get to Q1 is from Q0, right? Because that's the only transition into Q1 is from Q0, right? So that's how I could get to Q1. So it tells you something really special about X. But here's the kicker. Here's the kicker. We already have an invariant that tells us any binary string is in Q0 is one of the active. Remember, X is a binary string, right? Sorry, I'm getting really excited. Somebody's got to count how many times I said that. But when we consider, remember, Q0 is among the set of states that are active at all stages, right? So I can use that fact. So to prove the second invariant, I'm going to use the first invariant from our claim, right? So specifically on X. So by the first invariant, so I get for free from the first, so I get from number 1 over there on X. By the first invariant on X, upon reading X, Q0 is in the set of states upon reading X. So please note that the way I got this was because X has to be a binary string. That's how I got this. So that's how I'm using that over there. I'm using number 1 over there. Now, there's only 2 possibilities for A, so I'm going to do something akin to what I did for when I was proving this kind of claim on a DFA, as I'm going to exhaust all possibilities of A. We consider 2 possibilities for A. A is equal to 0 or A is equal to 1. Those are the only 2 that can happen with A. So we're going to have two cases. Let's head over here. So remember, we know that Q0 is one of the set of, it's a state that's currently among the set of states while I'm processing X. So now what we need to do is we need to look at the cases when A is equal to 0 and A is equal to 1 separately. See what happens. Does Q1 belong to the set of states in the appropriate case, or does it not? But the trick is, because I got my Explorer hat on, is remember, there's only certain states that you can get into Q1 from. We're going to use this fact. So we're going to call this one case A. So this is going to be A is equal to 1. Well, what can we say about the string in this case? Well, W has to end with a 1, right? So in this case, it most certainly should be in Q1 when we're done reading W. In this case, W ends with 1. Well, now that we know this as a matter of fact about A, well, let's just apply the transition function on Q0 reading 1. Well, Q0 reading a 0 is, actually not reading a 0, reading a 1. We want to read a 1. Well, what is this? This is Q0, Q1, right? Right? It either is still in Q0 or it has Q1, okay? So, but the thing is, it has Q1 in it, which contains which contains Q1 as expected for 2. Now, how about 1 and 3? 1 and 3. Well, 1 always holds, but 3, not so much, right? But the point is that we're not considering 1 or 3 right now. We're only considering the second invariant, right? That's why we broke it out by state invariant. So right now we're just proving that the second state invariant holds in the appropriate cases, okay? So let's consider the other possibility. But now here, it should not be the case that the state invariant is actually going to be true in the positive sense, right? It should be now that it must not be in state Q1 because it doesn't end with a 1 anymore, right? So notice W equals x0 does not end with 1. Now, this is where, so now we know on one side of this thing that yes, it doesn't end with a 1, right? So, think of my Explorer cap. What can we say about this situation? Observe that the only transition upon reading X to state Q1 on A is from Q0, right? And what can we say about the transition on 0? Well, it stays in Q0. And delta Q0 on what? 0, right? Not X, on 0, because we want to know where we're going, right? Like I said, we're trying to reverse engineer where we came from. We're using a specialized structure of the NFA to figure out where we could have possibly come from. So Q0 on 0 is, in fact, just going to only contain the state Q0, which does not contain Q1. Hence 2 has to hold, right? Hence 2 holds for W. So remember, the goal in this case was to establish, notice it doesn't end with a 1, so it has to be the case that Q1 is not among the set of states. Here we established it's not a part of the set of states. It's not Q1. Q1 isn't. And the way we knew this is because the only transition upon reading X to state Q1 had to have come from Q0. Because remember, I got my Explorer cap on. It means I know where I'm going. It means that I can't be coming from Q2. And I can't be in Q1, right? It's only Q0. So, that leaves us with one last case. And this one's a little bit more complicated. I encourage you to find other ways to prove this claim. I'm going to, based on what I alluded to earlier, I'm going to use an if and only if two-directional proof. So let's consider the following. So what we're going to do is we're going to prove this in each direction. So I encourage you to think about trying to prove this claim using an approach similar to the second invariant here. So give that a try. This isn't the only way to go about it, but you'll find that when you start dealing with situations where it's a little bit trickier to apply our observations about X based on the induction hypothesis, it becomes a little tricky. Sometimes it's best to kind of break it into the two directions of the proof because it's an if and only if claim. But you're going to notice very quickly that I'm going to use, for proving this state invariant on our induction step, I'm going to use the second case here. So on X specifically. So we need X on X. So let's consider this. So anyways, there's going to be two directions to the proof. Remember that I want to show the following, right? I'm just going to put it off to the side here so you remember. Remember, it's Q2 is in delta hat Q0W if and only if it ends with what? It ends with, I believe we want it to end with what? Ends with 1, 0, right? So to prove a two-directional proof here, I can start with this and work to get this, and then I can work from here to get this. So we're going to start by going this direction. So we're going to prove this direction of the proof first. So when Q2 is in delta hat Q0W, notice that again, this is going to be using my my little hat, right? I got my Explorer hat on. What can I say about if Q2 is in this set upon processing W? Where had to have come from? Well, look, there's no loops or anything here. It had to come from Q1, so processing X, I had to have had it where the active state was containing, sorry, the active set of states at that time upon reading X had to have included Q1. That's the only way I could have gotten to Q2 upon reading a 0, for example. Either way, it's the only way I could get to Q2. Like I said, we're trying to reverse engineer where we came from. So notice that the only transition, this is transition, it sort of melted in the microwave. Transition incoming to Q2 upon reading X is from Q1. So what can we say about Q1? Q1 is in delta hat Q0X. So it means that Q1 had to have been a part of the set of states upon reading X. So now that I know this, I have an idea what the form might look like, okay? So as Q1 is in delta hat Q0X by 2 on X, X ends with 1, right? That's what it says. That's what we got from the induction hypothesis. So we know it ends with a 1. That's what X ends with. Now, I pointed that diagram over there to help us. What's the only way I can get from Q1 to Q2? It's over a 0, right? Okay. So let's put this in words. The only transition from Q1 to Q2 is on 0, right? And Q2 is in delta hat Q0W. So to have this property means that it has to use this transition, right? But it's only on a 0. But what does that mean? Thus W ends with 1, 0. Right? So I started here. So if this, then that, right? So that direction of the proof is finished. Let's prove the other direction. So now I'm going to imagine I have a string that ends with 1, 0. I'm going to show you that Q2 belongs to the set of states upon reading string W. So consider string W when it ends with 1, 0. As W equals XA, both X ends with 1, and it has to, what else do we know? And A has to be 0. That's the form of the string, right? So notice the minute you have this, that it ends with 1, most of the work is done, right? You use the second invariant on X. As X ends with 1 by 2 on X, Q1 is in the set of states upon processing string X. Now, we just point our finger at the transition function, then we're done. Since delta, so I'm just going to use the transition function, since my delta is just sort of turning into music notes. Since delta Q1 on 0 is going to be the set with Q2 in it, by definition, so by pointing at the definition of the extended transition function, we can say that Q2 is in delta hat Q0 upon reading W. So that proves both directions of the third invariant, establishing the third invariant holding for all strings of length n plus 1. Hence, the statement follows. For all strings of length n plus 1, completing the induction step. Now, let's just invoke the principle of mathematical induction, and then we're done, right? Then we've established all three invariants, because the principle of mathematical induction now will state that all these things that we established, they'll hold for all n greater or equal to 0. Therefore, by the principle of mathematical induction, the statement holds or is satisfied for all strings of length at least 0. And that completes the proof. Piece of cake, right? So remember, the whole idea here was identifying the state invariants. Then what we did was we went through and proved each of the state invariants for the induction step upon completing the earlier parts of our induction proof. Since we didn't really have a good idea of where we could come from in each one, I broke it up by the state invariants themselves and reverse engineered where x would have been, so that I can use properties of x and infer properties of x. So we're not quite done yet, though. We have one more thing that we really have to do. We're not quite done yet. So we haven't really proven the correctness of the NFA quite yet. We haven't finished the proof for proving the correctness of M-end. Here's an argument that we're going to use now, the last step in our proof. So keep in mind, this proves the lemma. This is now a new part of this. If you need this to be in your proof of proving the correctness, I'm going to give you the argument first, then I'll state the theorem. We observe that the final state of M-end is Q2. Then it follows that any string W accepted by M-end must follow that Q2 is among the set of states upon processing string W. That's what this means, remember. Therefore, what can we say? By our lemma, any string accepted by M-end, I was about to say W, by M-end, if and only if W ends with 1, 0. Thus, now we can state our claim. The result. So here's the theorem. Is that the language of M-end is equal to the set of all binary strings such that W ends with 1, 0. Thus, we have established the correctness of this NFA. So, are there any questions? I see some pretty epic spam in the chat. But no, I think we're doing okay. Are there any questions? Any questions at all? Because that's the last bit of my material for this week. We actually got through everything this week. Are there any questions at all? But yeah, the big thing to keep in mind when we talk about this whole proving the correctness of an NFA is just, if you want to use state invariants, you got to be careful about how you design your NFA so that it's easy for you to know where you come from in a given state. So it's easy to kind of reverse engineer where it had to have come from. But you'll notice that the way I prove the claim, I rely on other cases of the invariance over the string X. And the reason, it's not really that surprising that this would happen, because it's all about reverse engineering where you came from. Well, to get to Q1, you have to come from probably Q0 at some point. To come from Q2, you have to come from Q1. It's not very surprising that that would happen. But it's something for you to think about. Imagine you consider a much more complicated one, like our two-pathwayed one where we detect cat or tack. Try thinking about how that would affect an NFA like that. But yeah, if there aren't any questions, I think this is a great place for us to stop for today. So just a couple quick things just to mention before we go for today is, if you're wanting access to the examples and my notes, they will be available later today on Patreon and Subscribestar at the supporter level, the supporter access tier, which is as little as about $5 a month, which is, it's a real bang for your buck. There's not a whole lot of options like that exist these days. That's at least what's available at this time. So please consider supporting our work here at Page Wizard Games Learning Entertainment, and support me, keep the lights on. We have ourselves a blast on over here, and I hope that we can continue keep having our fun here, learning all about computer science. So other than that, please check out the survey or questionnaire I have about availability for live streams, whether it be the gaming show or entertainment show or our live lectures. Also, I give a place where you can give some feedback on topics that might interest you. So I'll say thank you so much for coming on out. And of course, tell your friends to come join the fun. The more people come on out, we have a blast. The other week, we had quite a few people hang on out for our gaming stream. It was just wild. I was making some wild hentai noises, okay? We're not going to talk so much about the details on that one. You maybe have to check it out, but it's definitely not for small kids, that stream. No, don't. If you're a parent, don't have that one on, okay? So say thank you so much, everybody, and have yourself a beautiful day. I'll see you later.